Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the very good stuff. This is the AAS Journal Author Series. And I'm super happy to have Benedetta Veronesi with us today. Ah, I blew it.
It is okay. It is okay. No worry.
You say it. You say it.
Benedetta Veronesi.
Oh, whoosh.
It's okay. It's okay.
That's fantastic.
Hi, everyone.
Hi, everyone. Benedetta, where are you at? What's your geolocation?
So now I am in Lyon, in France. I moved here recently. Yeah.
So you took a new position?
Yeah. So I started my first postdoc at the École Normale Supérieure in Lyon. Before I was in Milan at the Universit degli Studi di Milano. Yeah.
Very cool. Very cool. And how is the summer in France on this July 6th?
So I would say that these two past weeks have had a lot of rain. So not really summer. Actually, some days it is a bit cold, but it's okay.
It's a different summer.
Yeah.
Very cool. Very cool. I thought, that looked like a sculpture over your left shoulder, but I think that's a cat tree.
Yeah, it's a cat tree. Actually, I think my cat is living in a small hammock. Yeah, I don't know if you have seen it. Yeah.
Oh, you have one or two cats? Yeah. You have one cat?
One.
Cat, very cool. What's his or her name?
Mirtilla.
Mirtilla. Very nice. Very cool. Well, I hope she's enjoying the summer in France there. So.
Yeah, I would say so.
Very cool. Benedetta, what do you like to do for research? So
currently, and also in my PhD, I worked on protoplanetary disks, and more specifically, I like to study from a numerics and theoretical point of view what did happen inside these protoplanetary disks, some mechanisms that are involved in their formation and in their evolution, and also to understand how we can explain the observation that ALMA is doing, that also Sphere on the Very Large Telescope is doing. So try to understand from a theoretical point of view what is happening inside these disks, and also try to explain how planets at the end will form inside these disks, because exoplanets have been detected like a lot in these last years. And so the idea is to connect the environment where these planets form and the actual final distribution of exoplanets that have been observed.
Very cool. Nice. And that is going to bring us to this super lovely APJ letter on a dynamical measurement of the disk mass in Elias 227. And Benedetta, take us away.
Yeah, thank you for having me here. And first of all, I would like to thank also my co-authors that are listed in here. And also I would like to highlight the fact that this work has benefits from funding from the RISE Dustbuster project from the EU. And thanks to this program, we were able to, especially as a young scientist, young researcher, we're able to travel, to meet, to exchange experiences, knowledge. So I think this work was super great in this sense, because it allowed to get in touch with other people, with both young and senior scientists. So yeah.
Very nice.
This for starting.
Good.
And then I would say that this work has been motivated by a very important question in our field, which is how massive are protoplanetary disks. Indeed, I mean, knowing the amount of mass that is present inside these systems is very important, because it allows us to determine the amount of material available for the formation of planets, and also to understand how massive are the system will allow us to better understand the process by which these planets were formed, and also the process through which these disks evolved. We can have different processes during the disk evolution, but knowing the mass is super important, and because we can end up with different scenario depending on the disk mass. Yeah. Yep. So in particular, we focused on a specific disk in this work, which is Elias 227. Elias 227 is quite, I mean, it's a 0.8 mega-year young stars. And it shows two large-scale spiral arms, which has been detected firstly by Perez et al. In 2016, and more recently also by Andrews et al. In 2018, and by Teresa Panicchi et al. In 2021. Actually, this last work is the paper companion of this one, because we rely on data that have been derived, that have been obtained in this work.
Okay.
So these two large-scale spiral arms are actually an hint of something specific, something peculiar happening inside this disk, and which is the fact that this disk could be a self-gravitating disk. What does it mean? This means that the disk is massive enough to like excite a gravitational instabilities inside the system, so that it can be visible as a sort of waves, and more specifically as spiral waves. Also, another hint to the system being self-gravitating is given by the fact that in the literature, the disk to star mass ratio have been estimated around 0.3. And for a disk to be gravitationally unstable, it is important to be like around 0.1 or more. So okay. This is a huge hint of self-gravity being important in this system. More specifically, what did we, from where do we started in this work? We started from the velocity data that have been obtained by Panicchi Carreño et al. In 2021. That work, they observed the system looking at the gas, not only in the dust, because the spiral waves are observed in the dust, typically in the dust continuum. But in this work, it has also been observed in the gas, which is very important because it can give us some information about the kinematics, that it's what is happening, kinematically speaking, inside this system. A first thing that I want to highlight is that in this companion work, it has been shown that this system shows an asymmetry between the east and the west side. We should keep this in mind. Okay. And so starting from the velocity data that have been obtained, we were able to, so our aim was to fit this rotation curve with a model, with a theoretical model. So if we go to equation 1.
Rotation curve, okay.
Okay, it's a bit slow. Okay, now I see it.
We have a little bandwidth.
You can see that there are different terms that enter in the game, in the play. So the first one, the right-hand side of the equation is the disk contribution. Then we have the star contribution, and then we have some pressure gradients. We can, I think, for this chat, for this chat, we can focus on the first two terms, which are the most important one. So usually, what people has always done is to neglect the disk contribution, because generally protoplanetary disks are assumed to be much less massive than the star. So right. We can neglect this term. But what if the disk is the disk gravity is important? So this model has also been applied to active galactic nuclei in the past, and it worked. So we decided to give it a shot for also protoplanetary disks. Also, the disk that we decided to look at is a strong candidate for self-gravity, so it was the perfect shot. Yeah, I would say.
Good.
We can then go to figure 1.
Figure 1. So stop that disk. We'll get some results and figure 1. All right.
Okay, so here you can see in all 4 panels the gray markers. The gray markers are the data that have been derived by Panechi Carreño et al. In 2021, and the curves represent our fit. So we have done different fit. So we have done both a Keplerian fit and a self-gravitating fit. So in the Keplerian model, we just consider the star contribution, while in the self-gravitating model, the star and the disk contribution.
Okay.
So in this plot, the fit has been done simultaneously for the east and for the west side, for the east and for the west side. So here I'm showing the results in separate columns for different isotopologues. So in the upper panels there is the 13CO isotopologue, while in the lower panel there is the C18O isotopologue.
Okay.
And but the fitting procedure has been done simultaneously for the west and east side of the disk.
Yes.
And in this case, what you obtain is that the difference between the 2 models is actually very small, but we have a difference, and also by looking at the I would say at the chi-square and the difference between the chi-square, what we get is that we have that the self-gravitating model better reproduced the data. So this is a first hint that actually self-gravity could be, and apparently it is important in this system. And more specifically, I want to say that in this plot, the red and the blue line are the dashed line are the fit done. So it's the Keplerian model where for the red one we have the actual mass derived through the fit, through the Keplerian fit, while the blue one is just the Keplerian model. It's not a fit, and it's the Keplerian model using as a mass the mass obtained in the self-gravitating model. So we can see that the self-gravitating model goes from the blue curve to the red one. Okay. And also, so I would say that this is the first result that we obtained, but knowing that that there is an asymmetry between the east and the west side, and also, if now we don't have the image, so we don't put the image in this paper, but if you go to check in the Panechi Carreño et al. Paper, you can see that the east side is the more absorbed, the cloud absorbed. Okay. And you can see this also here by looking at the error bars. Error bars for the east side are larger with respect to the west side.
Yes.
So one can think, okay, we should trust more the west side than the east side. This can be an option. So to follow this idea, this thing, we decided to also fit separately the west and east side. So if we go to figure 2.
Let me ask one question.
Sure.
On the data here, does the east side and the west side each have a spiral arm, or are the ALMA observations well enough resolved so that you exclude the spiral arm from each side?
No, so basically the spiral arms are observed in both sides.
Okay.
Yeah.
Okay.
But it is important to remember that the spiral arms are observed in the dust continuum, while we are looking here at the gas.
I'm good. Thank you. Okay. Figure.
So we can just stop a little bit on table 1, where we can see a bit more in detail, quantitatively, the results that I've presented in figure 1. Sorry. So you can see that. So we also did. Okay, I didn't. Yeah, what we did. Sorry.
Have some more.
What we did is a combined fit where we fitted simultaneously the east and west side, and also the 13CO and C18O isotopologue. But then we also fitted separately the two isotopologues. And what you can see here is that the nicer results comes from the 13CO isotopologue, where you can see that the difference between the chi-square for the self-gravitating and the Keplerian one is actually larger than so if you look at the 13CO, yeah, exactly, it's larger than 0 and also than. So this is nice. It's larger than 1. This is nice because it is saying us that the self-gravitating model is fitting is the best fit to our data. Okay. I mean, the difference is not huge, but it's already something.
Yes. It's in the right.
So also, I mean, I didn't say that this before, but we also did a fit with the power law, with the general power law, and the idea was that if the index of the power law is like 0.5, we expect the fit to be Keplerian, the best model to be Keplerian.
Yes.
If the power law index is lower than 0.5, we expect the disk to be self-gravitating. And what we get here is that for the 13CO isotopologue and also in the combined fit case, the best fit for the power law index is actually less than 0.5. So this is the first hint that self-gravity is important in this system. So after having done this because this was like actually our first test, then we said, okay, we should go with the self-gravitating model and see what happens.
Nice.
So if we go to figure 2.
Mm-hmm. Whoop. Too big now.
Okay.
Okay.
So here we decided to plot this case. The fit has been done separately for the because you have also some figure in the appendix, and now I'm not I don't remember anymore what one we put it here.
Okay. Yes, have changed a little bit.
Yeah, the fact is that now sorry,
there's different model parameters here, by the way.
Yeah. So before I think before we fitted simultaneously the two isotopologues and the two sides, while here we fit separately the two isotopologue and but still simultaneously the two sides. Sorry. And in the table there is also the results from this plot.
Okay.
Pardonnez-moi, using a French expression.
Yes, all good.
So basically, also from this plot, I would say that the most important information that we get is that the self-gravitating model is the best fit for what concerns the 13CO case, specifically, and also it better reproduces the data of the west side. So this is like the main point that we can say from these results. So if we go then go a bit low, I would go for a moment before this I will go for a moment in the appendix.
Sure. We got figure 4, figure 5 in the appendix.
So it's a bit okay. So let's stop this first figure. So the first figure of the appendix.
Figure 4.
It's a bit slow. Sorry, I have to wait for
just the bandwidth. Just bandwidth. Okay, we're going halfway across the world. We have to have a little. We have no patience anymore.
Okay, so I think it is nice to see also from the corner plots that are, represent our fit results, that if we look at the fit with both the disk and the star, we can see that actually the disk mass is different from 0 within 2 sigma. So this I think is a thing that is like supporting our result, and it's like gives some strength to our result, because yeah, I mean, if it would have been like in 1 sigma or yeah. So I think this is nice, and this like is giving, yeah, is saying us that we are following the possibly, I mean, everything can change, but we are following possibly the correct path by saying that this disk is self-gravitating. So if you go back to figure 3. Okay. So here we decided to like represent in another way our results, to highlight what we found, and what you can see here is the residual obtained for the combined fit. So for the fit where both isotopologues and both sides have been fitted simultaneously.
Okay.
And the top panel represents residual for the 13CO, while the bottom one for the C18O. Left columns for the west side, and right columns for the east side.
Yes.
And points represents the difference between the velocity data and a Keplerian model, where the star mass has been obtained through the self-gravitating model. So this is the Keplerian model where we put as a mass the mass obtained with the self-gravitating model. The dashed line is instead the difference between the self-gravitating model and the above mentioned stellar contribution. So and you can see that especially for the west side, and especially for the 13CO case, the dashed line represents the trend. I mean, it's following the trend of the point. So this is another visualization, another way we can visualize our results, that is saying us this disk is possibly self-gravitating. At least the west side. I mean, I think to really understand what is happening inside this system, we have to understand what is causing this asymmetry between the two sides in the gas.
Yeah.
Because, for example, an idea is that it can, since it's still a young system, and some cloud absorption has been observed, this can mean that there is some material that is still falling on the disk from in one side. Right. So I think really understand what is happening can shed some light also on this result, and also can confirm or not what is our finding. So I think that this is the most important result that we have found. And also I would say that this result, I mean, the way through which we derived the disk mass is a new way that has not been used before. In the planet formation, in the planet community. And it is important to highlight this because usually disk masses are derived through some estimates, through some assumption on the, for example, on the gas to dust ratio. And but the dust to gas ratio is something that is not super known, so not super well constrained. And also disk masses are obtained by looking at the abundance of CO as isotopologues with respect to molecular hydrogen, but also the ratio between the ratio between H2 molecular hydrogen and CO isotopologues is not well known, is not well constrained. So usually estimates derived through these two methods are giving us a a lower limit. And I think that it's well known in the communities that if then you perform some additional models, and so by starting from this from the disk masses obtained with these methods, you cannot reproduce the distribution of exoplanets observed. You cannot reproduce. You cannot have giant planets. So the disk obtained are too low. The disk masses obtained are too low to then get the planets that you expect to form in this system. Okay. So finding another way, which is actually which is actually seeing in principle all the disk mass, not only a component. Then, because if you look at a specific component, then you have to like go back to all the disk mass, to all the disk, to all the disk mass. But if you find a way through which you can already look at all the disk mass, this is important because it can tell you something. It can give you a more precise disk mass estimate. So
very cool. Very cool. And then we concluded off with what the disk mass was. Very cool.
Yeah.
Benedetta, thank you very much for walking us through your lovely letter. And so where do we go from here? Let's say over the next 5 years, 10 years, 2 years, your choice. Are there additional ALMA observations coming? Are there other telescopes at other wavelengths that can help inform this? Are there other systems close enough where we could sort of repeat the analysis from Elias 227? And just where do we go over the next, let's say, couple of years?
So first thing I would say is that I think it will be important to strengthen this result and to understand to really see if there is a result. This procedure can be improved. Also, I think by deriving the velocity data in different way, because in this case the velocity curve has been obtained by looking at channel maps of series topologs. And by so the derivation of the rotation curve has been done geometrically with a geometrical method, but actually there can be more precise way of deriving the disk rotation curve, and this is the first point, because we are fitting data, so we need to really be sure of the data that we are fitting. Also, I think that it is important to here we also considered in the paper, I didn't mention them, but we also consider the pressure gradients. But they are not such a big effect. They don't. Their contribution is less important with respect to the disk and star mass. But I think, it is important to redo this procedure by fitting velocity data obtained in different way, because this can really say us you are doing the things correctly, or we should look at this better, or at this other thing better. So I think this is important. And also I would like to say that I think it is important to redo this procedure on other disks. So we are actually there are some works that is ongoing on other sources, and also we have applied for we also asked for ALMA time. I don't know if we still have to see if this will arrive or not, but I think this direction, I think this can be a nice direction where to go in order to get some more precise estimate for the disk mass, in order to understand if some disks that potentially can be self-gravitating are actually self-gravitating. So
yep, very cool.
I think this is the thing that I would say will be important in the next years,
Cool, very nice. I think there'll be lots of activity in this field over the next coming years, particularly thanks
Yeah.
to other things.
Yeah.
I think you'll have a very productive postdoc. Benedetta, I want to thank you once again for walking us through your lovely letter. And everyone, that will do it. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.